All right, I'm going to get started. So today we're going to discuss enolates, but I thought before I got started, somebody was asking me about the sort of chelate within dieball and how that takes place at sort of driest acetone temperatures, so super really cold, minus 78 degrees Celsius temperatures, and sort of asking about, I think it's one of those things we often don't really think about things that cold, right? It's not something that we deal with on a daily basis, so we normally think of things as being cold. It's a cold day, it's maybe minus 20 outside if it's horribly cold, right? But that's about the extent of it. But at minus 78, I mean, it's still, whatever, 200 something Kelvin, right? There's still energy there. It's just, you're just playing with relative stuff. And so a lot of chemistry is held at minus 78, in part because dry ice is, well, somewhat cheap, acetone's cheap, and so you mix the two together and you get this cold bath. And so it's just, from practical standpoints. All right, I thought I would show you another example before I get into enolates of another reaction that could be valuable within syntheses problems or whatever, that also sort of takes this chelate into play. And so we discussed that if you take say an ester and you treat this with, say, right, this is phenyl grignard, right, and this is effectively a reaction that you guys ran in the lab, first semester organic chemistry. What happens? It's going to happen when we take phenyl grignard and we treat it with some ethyl ester. Attack the carbonyl. Upon elimination, we're going to have this phenyl ketone. And then it's going to add it again, right? And the idea here is that ketones are more reactive than esters, and so if you have something like an ester and you're trying to turn it into a ketone, right, it's going to be very difficult, right? And so one way, if we wanted to make this compound here, and we started from this compound here, knowing the chemistry that we know, how might we go about this? That? It would be like a 3-step synthesis. So how would you make this? Right? You might imagine making that from the alcohol, right? Which would then allow this to come from aldehyde. And then whether you go down to the alcohol and up to PCC or whether you go directly with dieball, right? 1 or 2 steps depending. You can get there. So you can see it becomes a fairly drawn out reaction. If you try the dieball and the dieball, you just can't get it to stop the aldehyde, and you're stuck going to the alcohol, oxidizing back up to PCC, adding in the grignard, and then oxidizing back up. You can see that it becomes sort of a stepwise process. And so analogous to dieball, right? So how dieball would add in once. Grignards, there are ways for us to get grignards to add in once. So we saw that acid chlorides might be okay. Usually in that case you'd want to use, we discussed like going from the acid chloride, you might be able to use like phenyl copper lithium or something like that, right? The Gilman, that would be one other option, right? So if everybody sees what I'm sort of getting at, if you instead went to the acid chloride, then what you could probably do is use phenyl, sort of Gilman reagent, right? And that would get you to the phenyl ketone. But if what you want to do is, for whatever reason, right, there's other ways to go about this, And there are ways to get Grignards to do this through chemistry that doesn't necessarily involve Yeoman reagent type stuff. Say, for example, one of the problems with Yeoman reagent, right, is that you sort of always have a sacrificial equivalent, right? So you sort of generate this diphenyl copper lithium. So let's imagine whatever this alpha lithium that you made was really, really valuable. You didn't want to have to throw away half of it. You wanted it to all go in. So one way that you might be able to do this is to say, for example, make the Grignard. But again, the problem with the Grignard is that it becomes pretty steppy if you want to use the Grignard. So again, this just goes back to coordination chemistry, chelate, getting stabilized chelates. It's not a direct method like Dibol is, but it might cut down a step or two in the synthesis, and that's to take your esters and convert them to something known as the, I guess it's called the Wiener-Vamid, but apparently Steve Weinrib doesn't like it when people call it the Wiener-Vamid because it's, yes? So I'll show you some variability in a bit. So one is considered harder, one is considered softer. I'll answer your question. I wasn't planning on answering that question, but there's a good place for me to answer it in today's lecture. So what you'll do is you'll basically take the compound and you'll do a, and again, the conditions to do this, we'll just sort of keep it simple based upon what you guys have seen. Usually there's coupling reactions to do this. But just to keep it sort of in line with what we've seen, we know that we can take sort of esters, and we've seen this, and we can turn them into amides by basically using amines and some acid, right? And what would happen here, right, is that then we will get this amide, which is at least colloquially known as the Weinrib amide. Okay? And the thing about the Wiener-Vamid is, if you take the Wiener-Vamid, and again, at low temperatures, I think it's minus 78, it's been a while since I ran one, but if you take it and you run it with, say, phenyl Grignard, I'm pretty sure it's also minus 78, just like Dibol is. What happens is, when the phenyl Grignard adds in, we'll just draw it as the magnesium bromide salt. You know what, I'll draw it as the ion. Right, so ordinarily, in the case of an ester or something like this, you get this intermediate. Normally what would happen, right, is this would collapse back down. You might lose the nitrogen, or perhaps, under slightly acidic conditions, maybe it would go the other way, but in general, you would probably reduce back down and you would get to this. But what happens in the case of the Wiener-Vamid is you again get this sort of stable chelate. Okay, and so this is a stable 5-member chelate. And again, if you run this at minus 78, when you're done with the reaction after a certain amount of time, you'll then quench it. You'll sort of keep it cold. You'll quench it. You'll warm it up. You'll have effectively quenched all the excess Grignard. This will all fall apart. And then you will effectively get to the ketone. Okay? So I might have taught this just vaguely for students that had me in Orgo 1. I think it's simply because of the question that I just got. I thought it was worth revisiting now. I won't hold you responsible for this, but if you want to use it, a synthesis problem or whatever, it's there. But again, I think it's another example of sort of metals serving as sort of chelates to sort of stop the breakdown. And so this is very analogous to Dibol. Okay. I'll leave that up there for a second. Okay, so what we're going to focus on today, and tomorrow is going to be a lot of enolate and enamine chemistry. Formally, what we're talking about here is chemistry whereby these can be anything. We'll just say R1, R2, R3. So what a lot of the chemistry, what we're going to discuss today, again, those are, a lot of these R's could be protons and so forth. What we're really going to focus on today is chemistry whereby if you take this compound, you can effectively take and exchange out that proton. And I'll just say, usually it's an electrophile that we're going to treat these with. I guess I'll just stick with that. I'll just say E+. So we'll effectively substitute that position with an electrophile. And so this is really going to be the focus of today's class as well as Wednesday's class. Now, we've seen some semblance of enolate chemistry in Organic 1 to an extent. Those of you who took it with me might have seen it a little bit more because we did skip ahead a bit just to sort of introduce these things. But what you should have all seen is that ketones, right, generally in the tautomeric form with what's known as the enol. Right? And so, again, we saw this when you hydrolyze an alkyne, for example. Where else did we see this? We saw this the one place I can think where we learned it. I can't think of where else we saw it, but certainly we saw this, for example, when you take an alkyne, right, and you treat it under acidic conditions, you get to this intermediate, it breaks down to a ketone. I think there was somewhere else that we saw this. And we know that, again, these will undergo tautomerization. Yes? What? This one right here? Maybe, if this does it. So we've seen in the past that this sort of equilibrium exists, that this one is the major one, but at equilibrium, you can get this sort of, some equilibrium where you might have, you know, who knows, I'm just going to say 1,000 molecules of this in solution, and maybe 1 molecule of this in solution. But oftentimes chemistry will be driven through the enol form. And one place that we saw this, right, is if you take this molecule and you treat it with bromine, you'll get alpha bromination. And again, the mechanism is simply, it's an alkene, it's similar to the chemistry of an alkene, right? And so we can draw it as that bromonium, for example, and obviously at this point what's going to happen is it's going to open up. Right, and then, you know, perhaps the bromide will come to deprotonated or something will come to deprotonate that and get to the sort of alpha bromo ketone in this case. And many of you have heard the sort of story that, again, this reaction will work. This is not just sort of in theory it works, and my story that I often tell students is a good friend of mine who's well on his way to being a big shot professor at a major research institute when he was a first-year graduate student, had run a reaction in bromine, and again, we use acetone for our squirt bottles and stuff like that, and so there's an acetone waste bottle, and he poured the bromine into the acetone, and it just erupted everywhere. It was very exothermic. And so I was downstairs teaching, and he comes down, and he's in like sweatpants and stuff like that, and he says, you know, Ryan, you know those showers that no one ever uses? So I just had to use one. So bromine and acetone do react, bromine and ketones do react, and they're actually fairly it's a fairly exothermic process. Now, translating this forward from the enol, the chemistry that we're going to focus today is on, instead of going through the enol form, what we're going to focus on is actually going through the enolate. So we're going to do that today. And then, depending on how much time, we'll either work on enamine chemistry at some point after that. But we'll focus on enolates. And so, for starters, we'll focus on enolates, and then I'll introduce enamines in a moment, or maybe after I'm going through all the enolates. Probably makes more sense. Okay, so an enolate is effectively the deprotonated form of the enol. Right? And so as it turns out, if you take an enol, if you take a ketone that has an alpha proton, and you treat that with a strong base, what's going to happen is you're going to deprotonate that, right? And this is stabilized by sort of a resonance form, right? And so because of that resonance stability, the pKa of an alpha proton, right, is going to change on us from somewhere, your standard, methyl lithium, for example, has a pKa of like 50 or something like that, something fairly high. The pKa of an alpha proton to a carbonyl is actually much lower. The pKa is somewhere in the, it's going to 10, we'll just say somewhere around 20. So it's significantly lower, significantly more acidic than your standard carbon bonds. And again, why? Well, I just showed you, right? It's because of this resonance stabilization, right? You can effectively take that negative charge and delocalize that onto the oxygen, okay? At this point, we have two forms, okay? And again, as you might imagine, just by looking at these, this is probably the one that exists more, because that oxygen is more electronegative. That's the one that's going to hold onto that negative charge a little bit more. But really, there's chemistry that's involved where you can take electrophiles and either do what we call O-alkylation or, and what we're going to focus on today, or today's class, is going to be C-alkylation. Okay? And so then I'm showing this just so that you guys know. Some of you might be asking, well, why can't you alkylate the oxygen? Well, you can, but oftentimes what happens is we're going to do C-alkylation, and there's different reasons behind these. There's these sort of molecular orbital, or at least sort of ideas called sort of hard-hard interactions versus hard-soft interactions. We're not really going to see this much at all. So for your guys' own sake, what you can sort of think about this is as a thermodynamically controlled alkylation. You have these two, right? But the product that results from this has the ketone. And as we've seen, ketones, for example, the enol ketotautomer, right, the ketones are generally more stable. So just so that you guys can conceptualize it, just think about it as being the thermodynamic product. It's not exactly the way it is, but at least in terms of you guys being able to rationalize it, just think about it as a thermodynamic product. And so what we're going to talk about, so what we're going to talk about today, I'll just erase this and redraw, but what we're going to talk about today is a lot of chemistry that simply involves literally this nucleophile, right? So that's all, what we've seen Grignards react with things, we've seen hydroxides react with things, we've seen lots of different nucleophiles. Really, all today is going to be is examples and uses of sort of enolates as a nucleophile. Okay? Make sense? All right. All right, so, okay, so we were just sort of discussing different bases that you could use. So, given the pKa value that we have, what we're really going to discuss today is two different types of enolate. So I'll just break this down further into two different classes of enolates that are a little bit different based upon pKa value. So in general, if you're just trying to make an enolate of an alpha proton to a carbonyl, just your standard one where the pKa is around 20, the base that we're going to use to deprotonate this is generally the sort of go-to bases are, the go-to bases is LDA, which is lithium diisopropyl amide. But in general, it's just amide bases. That's often the go-to bases, is these sort of, in this case, lithium. This is abbreviated LDA for lithium diisopropyl amide. Okay? And so this is the base that's almost always used. The reason it's used is that it's bulky, so it's got these two flanking isopropyl groups on. So as you can imagine, like you might get nucleophilic activity, right? So as we've seen, bases can also often be nucleophiles and vice versa. If you want something to only act as a base and not so much like a nucleophile, you'll do things like bulk it up, right? So that's why LDA has these diisopropyl groups on here. And so if you do this, what that'll give you entry to is the enolate. But the other class that we'll focus on, again, is you sort of look at this pKa of 20, and the pKa of LDA is, I think it's like 28, we'll just say somewhere around 30. So again, the point is that it's more basic than this. The other class that we'll discuss a little bit today is going to be, I'll just say X, carbonyls where you have sort of this extra carbon, where you have these sort of 1,3-dicarbonyl species, right? And so in this case, the pKa is much lower, okay, somewhere around 11. And so at this point, you can start beginning to get to slightly weaker bases. So you don't have to go all the way up to LDA to get this to react. You can start to use bases like your ethoxide bases, potassium carbonate. Maybe we'll just say one that you guys have seen, potassium t-butoxide will work just fine. Again, pKa of potassium t-butoxide is at 17, right? So you can get away with weaker bases in this case to deprotonate this. And part of the reason, well, the reason, right, is why. Why would this enolate be more stable than this enolate? Well, yeah, it's the second resonance, right? So we can either have the resonance go this way, or we can have the resonance go this way, right? And so for these reasons, this is the other class of sort of enolates that we'll see, and it's just worth noting that it is more acidic. People generally like using this. The relative acidity here will come up. I was going to say in a little bit, but now I'm thinking maybe I'll just show it now. So I'm going to jump ahead in my notes, because now is probably the time to show this. Now I'm thinking about it. Okay? Now, as you can imagine, in all these cases, simply what we're doing is we're making a nucleophilic site. But if you have a standard ketone, let's just say R1 and R2, right? If we try to deprotonate this, we're going to get a mixture of enolates, right? So we just say 1 LDA, 2 electrophile, okay? What's going to happen in this case is that you're going to get a mixture this as well as the other one. Perhaps a bunch of permeations in between, where you get addition. So the issue here that we're going to see in terms of enolates is because a ketone could have alpha methyl groups on both sides, what that may lead to is a situation where you get some regioselectivity that needs to be addressed. And so we'll discuss, what we're discussing here is a couple different ways that we can sort of overcome this. One of these ways, okay, involves taking advantage of this pKa difference, okay? And so, and again, we'll probably get we'll sort of see how we can translate this into the chemistry as we start learning more of the chemistry, but I think I'll show it now and then I'll probably show it again later. Put that down there. One of the ways that you can do this is by having on one side or the other, you can have a sort of a carboxylic, sort of some type of a group installed. And we'll talk about how to make these in a little bit. The point is that you can have these, this ester here, okay? In this case, you wouldn't treat it with LDA, right? Because now it's more like this one, right? Because it's got the proton that's flanked by the 2, right? And so what you can do in synthesis at this point is treat it with a weaker base, let's just say butoxide, for example, right? Now you're going to get that selectivity for that central carbon there, and then when you take this and you treat it with your electrophile, okay, well great, that's not what I want to make, right? But if we wanted to get rid of this group, what did we learn a couple classes ago about how we might be able to chew off this group and get to this? Right, so the first step will be saponification. So let's just say sodium hydroxide water, for example, or perhaps acidic saponification, some type of hydrolysis of this to the carboxylic acid. Right? And then what do? We're just going to heat it, right? And so what we'll do is we'll heat this. What that'll do is that'll do this decarboxylation that we discussed. Right? That's going to go to the enol form. Right? And then this is simply the enol of that guy up there, right? So if you want to get control, and we'll discuss how to make these a little bit, and we'll come back to this and reiterate this. This is an important point where these relative pKa's come up, right? In a situation where virtually both these would have the same pKa, you might not be able to sort of get away with deprotonating one over the other. As we'll see, one strategy that you can use, and we'll teach you some chemistry that'll help out in this regard, is leveraging these pKa's. Is that in my ear, or is that actually sounds like R2D2? So what's going to happen here is you just sort of have this extra electron withdrawing group here that's going to make that much more acidic. The one other place that we'll see this, and so since I'm showing you this one area, I'll show you the one other area, and then we'll discuss different types of electrophiles that we'll treat them with. So this is one strategy for regioselectivity issues. The other strategy that's perhaps a little bit simpler is if you have a ketone like this, right? Some type of symmetric ketone, some type of substituted ketone, where you've got two alpha carbons, and one of them is more substituted than the other, right? We can imagine products that would arise either by attacking at the one side or attacking on the other side. And as it turns out, we've got ways that we can do this as well. So I just want to sort of introduce the generation of enolates. I think this is perhaps a place that's worth describing this. And in truth, there's some different bases that we like to use in practice. But I think the book at least gives a good way to sort of think about doing this chemistry. In both these cases, really what it comes down to is the generation of an enolate, right? And so whether it's this enolate or whether it's that enolate right there. Okay, so those are the two different enolates. Now, if I were to ask you guys, this is perhaps one of the first times we're going to see sort of thermodynamic versus kinetic control. Having a product that can arise through kinetic control. We've seen this a little bit with, well, no, we've seen this. We saw this with elimination to a certain extent, right? If we right, and we've seen something very similar to this in the past for regioselectivity, right? If we want to do elimination chemistry, right, and we have a couple options. One of these sort of represents the kinetic product, and one of them sort of represents the thermodynamic product, right? Which one is the kinetic product? The one on this side, right? And what we do to make the kinetic product form, right, is we give it a big bulky base, like we've seen potassium cubietoxide or something like that. And the idea here is that the more accessible proton is taken off, right? So it becomes the sort of kinetic product, if you will. Right? And so that's going to lead to the kinetic product. This is perhaps a misnomer because this could also perhaps be rationalized as a kinetic product as well, although it is a thermodynamic. This is perhaps just to sort of think about this a little bit more. But if we use a smaller base, like sodium, let's just say sodium amide, for example, right, we're going to end up leading to what would then be the thermodynamic product. And again, this might not entirely be the best way to at the actually core of it, but I think in terms of conceptualizing it, this makes sense, right? The energy barrier, it turns out, to go to the more stable alkene, right, is going to be preferred when we're using a base that doesn't really have any relative selectivity. You know, like this amide's small enough that this proton and this proton both seem the same, right? So we saw this last semester. In this case, we're going to do something a little bit different, and it's certainly more thermodynamic versus kinetic control, in part because, unlike this, where equilibration isn't necessarily taking place, which is often at the heart of thermodynamic control, here we are going to sort of leverage equilibration, right? So if something equilibrates, it's going to go to the lowest energy, right? So if you use, say for example, if you take this compound and you treated it to LDA, okay, LDA is a big bulky base, right? What's the first thing that's going to happen? It's going to deprotonate. And which proton is going to be more accessible for a big bulky base? The one on the left or the one on the right? Right, so the one on the left. So LDA, if you take a compound like this, you treat it with LDA, the first thing that's going to happen is you're going to get to this molecule here. Okay? Now, let's pretend we're in a situation, right, where this molecule can react, right, and you give it enough time, right, and you allow it to equilibrate. You can imagine a scenario where this enolate, right, begins to deprotonate, right, the alpha proton on a subsequent additional molecule, right? So if you give this time to equilibrate, eventually, over time, what's going to happen, right, is that you are going to begin to have this compound here become the more thermodynamically stable molecule that I'm showing you there. I want to make sure I get this right. Okay? Okay, and so if you take this molecule and you treat it with LDA, right, it's going to get to here, okay? Now, if you have a large excess of LDA, right, this molecule is already charged. This proton here is now no longer acidic, right? You've got this charged molecule, that proton is not going to be acidic. So if you have a large excess of LDA, you're going to generate this molecule. I need more boards for this. Explain this. So with excess LDA, what's going to happen is you're going to get to this molecule here, and generally you run the reaction, you sort of add it, you don't let it sit around too much, you added an excess of LDA. This proton's kind of safe because, again, it's not going to get deprotonated by another version of itself. And then you simply take this and you treat it with your electrophile. What's going to happen is you're going to get that product. So that's if you have an excess of LDA. If you have sort of substoichiometric LDA, so let's just pretend like 0.9 equivalents. Okay, so 0.9 equivalent, some amount where there's a little bit excess ketone going on in there. What's going to happen is you're going to now begin to allow this type of equilibration to take place. And again, this could deprotonate this proton, it could deprotonate that proton. It's a dynamic system. But over time, what will begin to happen is the equilibrium will begin to favor the enolate that's more stable. Now, why is this enolate, I don't know if I said this, why is this enolate the more stable enolate? So it should be fairly obvious why this proton is a kinetic proton, right? It's the more accessible one. Why is this enolate the more stable enolate? It's more substituted, right? It's the same reason why we talk about alkenes in terms of the more substituted alkenes forming. Okay, and so if you take this and you now treat it with some type of electrophile, now you're going to get substitution on that side, okay? So as we go through some of our reactions today, really what chemistry is going to be focused on is going to be enolates reacting with different electrophiles. But I figured it's sort of worth it to, at the very beginning, just sort of introduce the different types of enolates that can sort of be formed in some of the regioselectivity. And so a lot of these issues about regioselectivity, as we'll see, could apply to many of the different reactions that we're going to sort of learn today. Okay, and the very first reaction that we're going to learn is going to be one called an aldol reaction. Okay? And what an aldol reaction is when you take a ketone, okay? You take some type of a ketone, and you're going to treat it with the base, LDA, and you're going to subsequently treat it with an aldehyde, okay? Okay? So let's just think about, again, we should all be able to rationalize and at least predict what type of reaction is going to form, right? This shouldn't be, well, this is perhaps the first time that you're seeing this aldol reaction. At least understanding the chemistry that's involved, you should be able to predict what the product is, right? So the first step in this reaction is going to be what? Right, so LDA, protonate, okay, and so now we've got our enolate form, right? And now what's, again, we've been talking about the electrophiles. In this case, our electrophile is going to be the carbonyl, right? In this case, the aldehyde, right? And so, as we've seen in the past, even earlier today, when our carbonyl is our electrophile, you're basically going to break double bond, and what will be left behind is you'll go from a carbonyl to an alcohol, right? So when you take this and you treat it to the aldehyde, what's going to happen is you're going to end up with this beta alkoxide, okay, and then once you work this up, you just take it, you just treat it with water, okay, and what's going to happen is you're going to get to beta hydroxy ketones, okay, so at the beta position, you have hydroxide, and again, we'll see it's fairly prevalent molecule in sort of literature, and so aldol chemistry is a very widely used transformation. In part, as you might imagine, you're sort of generating molecules you've sort of created. Again, carbon-carbon bond, that's one of the most important things, right? So the aldol reaction allows us to create a carbon-carbon bond, and then the other thing that it sort of leaves us with is two functionalities that we've already seen have a lot of versatility in terms of building up groups. So you can imagine you make this molecule, sort of create a carbon-carbon bond. What you have left behind is an alcohol, and we've seen all this chemistry that you can do, functionalize alcohols, and furthermore, all this chemistry that we've seen to functionalize carbonyls as well. Okay. Now, it turns out there's another reaction that's just an extension of this that's fairly, I'm just going to erase this right here, and it's called an Outlaw Condensation. You know what, whatever, I'll confuse you guys if I don't do this. So, aldol condensation is the exact same thing as an aldol. Except what happens is, following the reaction of the aldehyde, what you're going to do is you're going to take the reaction, you're going to treat it to dilute, usually sort of acidic conditions, so mildly acidic conditions. I'm trying to think if it's aqueous or not. We'll just say dilute acid. And what that's going to lead us to is what we call sort of an alpha beta unsaturated carbonyl. Okay, so we basically have this alkene there. Why do we call it alpha beta unsaturated? Well, when we talk about saturation in organic chemistry, oftentimes what we're talking about is a molecule being saturated with hydrogen. Okay, so if it's unsaturated, that means that it's effectively an alkyl chain, sort of that's effectively lost an equivalent of hydrogen. Yes? So I'm going to go through the mechanism in a second. Okay, now, as we'll see, and this will become a theme specifically as we start moving forward past this chapter, conjugated pi systems, okay, are actually very stable, right? Electrons in general, we often think about negative charges, for example, in resonance forms, stabilizing negative charges. Molecules in general can be stabilized when you can have extended systems, pi systems for example, that will allow charge distribution along a sort of a greater extent. And this is how I always like to think about electrons and as being sort of claustrophobic, if they can sort of break from their restrictions of 2 atoms and to go to more, they kind of like that because they can sort of move around a little bit more. So that's the idea of sort of allowing flow. Again, it sort of explains to an extent how resonance stabilization can be helpful as well. So the product of this after the aldol, right, is this alcohol, right? So we already saw the mechanism of that before. And again, so the drive behind this process is thermodynamics. Okay, what's going to drive this process is going to be that by generating a conjugated dienoic system, that's going to be a more stable overall complex. And so what's going to happen here is if you treat this with dilute acid, and again, I'm going to sort of show it in strong acid, but the point is that this will go fairly quickly, even with sort of things like acetic acid and so forth. You can at least think about this mechanistically in one of a couple different ways. Okay. One way that you could sort of think about it that might be best. There's many different ways you can draw this mechanism. I'm going to show one, and then we'll sort of discuss, and if you guys want to ask about, well, what if I did this? Right? So we're going to have this sort of protonation of the water, okay? Now, as we've sort of seen, right, in this case, might the conjugate acid be strong if you protonate this? Maybe, maybe not. But remember, this enol will exist, this ketone will exist in at least part through the enol keto tautomeric form. Right? And at this stage, what you can now do is eliminate the water. And then simply you'll deprotonate that group and you'll get there. So this is just one example of how you can draw the mechanism. But formally, what it is, you can imagine deprotonating doing like a E2 elimination process instead of going through the enol. That's kind of what I was debating how specifically to draw it. I think this is perhaps more consistent with the acidic conditions, because the question is what's the base length. But it doesn't really matter at the end of the day which one of those two is going. The more important point here is that this is driven. It's driven by thermodynamics. So again, this is once you deprotonate, is a much more stable species. And the other point that I wanted to make about this the other point that I wanted to make about this is one of the ways that you can sort of rationalize what's going on here is that it's called a condensation, right? And so we've seen, and we're going to see a bunch of reactions sort of called condensations, okay? And if you sort of think about condensation, what is condensation? Sort of involves water, right? We usually think about like condensation as sort of water on a, right? You're sort of generating water, and so in this way it's kind of a condensation in that you're sort of losing water. Yeah?
There. What is going on?
The keto polymer?
Water and so is it the alcohol about the acid and then they use the electron?
So these are just tautomerizations. These are just tautomeric forms of one another. Okay, let me draw it a different way. Okay, I'll draw it a different way. So another way that you can think about it, if I draw some type of conjugate base, let's just say acetic acid, for example, right? This would be way in that direction, but over time, it would drive the reaction via Electrophile principle. You could imagine this as being an elimination process. I drew it as the enol form simply because I think that's probably more likely what's going on in this. I don't think that it's really genuinely an E2 elimination process, and I don't really feel like, I don't know, just my own sort of sense of chemistry, I don't really want to be generating a carbocation that close to a carbonyl, even though that might be what's going on. That's why I think it's probably more likely going through the sort of enol form. But however you can rationalize it, the point is that it's an elimination. However you package it up, that's what it is. It's an elimination of water. So you can draw it through the enol. That's how I like looking at it. You can sort of draw it as a standard elimination process as well. In that case, again, if you went through the carbocation, that's fine. I didn't feel comfortable doing that. Okay, so again, there's your first couple reactions with carbonyls. Okay, so aldol condensation. We'll show two others that sort of relate to this, and then I'll do a couple extensions. So we're going to come back to these. Somebody asked about cuprates and how cuprates and Grignards are different earlier. And so I'll sort of show an example of that within alpha-beta unsaturated carbonyls. So first, another class of reactions, this is going to involve nucleophilic addition into enolates, sort of involves this. So how should I introduce this? You know what, before I go into Michael addition, we're just going to talk about alpha-beta unsaturated. This will answer this question from earlier. Now you know how to make those. Okay, so alpha-beta unsaturated carbonyls. I'll just go ahead and draw that exact same one there. Okay, this is the molecule. What we'll see is that these molecules are electrophiles, and they can serve as electrophiles in a couple different ways. Okay, so in general, when we start thinking about the reactivity of, say, for example, a ketone, right? One of the ways when we first start to learn about reactivity of ketones as electrophiles is to look at the resonance form. Okay? And so we've sort of seen this in the past a little bit with ketones, right? If you're uncomfortable adding at that carbon and then breaking the carbon-oxygen double bond, one way that you can perhaps react and think about mechanistically reacting with ketones is by thinking about the resonance form, right? Where there's a positive charge here, okay? And it turns out that if you take, a molecule, let's just say phenyl Grignard, and just for arrow purposes points. So if you take this phenyl Grignard, I'll just draw it as the ionic form to see the reactivity, and you took this phenyl Grignard and you treat it with this carbonyl, what's going to happen is you're going to get that addition there. Okay? And the product in this case will be following workup, right? And so this might be what you would expect, right? You take a ketone, we've learned ketones react with Grignards, alkylithiums, they're going to add in terms of what we would call 1,2 addition, okay? But in the case of alpha-beta unsaturated compounds, one of the things that make them sort of special is that there's also a good deal of positive charge actually on the beta position as well. And so this is the sort of carbonyl, This would be the beta position, and we can rationalize that through resonance form, right? So if we think about this molecule, this is the other resonance form. We can sort of draw it as that resonance form we've seen right there, okay? And so as it turns out, there are nucleophiles that will, instead of adding 1,2, will add 1,4. And in fact, the 1,4 addition is generally like what we talked about before, sort of hard, soft. The sort of thermodynamic product is often driven by addition to that sort of carbon right here. And it turns out that whoever asked the question earlier about the difference between Gilman and Grignard, it turns out that additions of Grignard's and Gilman reagents into alpha beta unsaturated carbonyls is actually one of the nice complementary utilities of these. Because if you take this molecule and you treat it to something like a Gilman, so let's just say phenyl Gilman, what's going to happen is, again, following workup, that you're going to get that compound there. Okay, so the addition, what we would call 1,4, okay, meaning 1,4, 1, 2, 3, 4 versus 1, 2, is going to depend upon the type of nucleophile that you're going to have. So if you have something that's a little bit harder, like an alkyl lithium, something that's much more charged, it turns out that these things are going to add to where there happens to be a larger percentage of positive charge character. Where that positive charge character ends up being is at this resonance form here because it happens to be closer to the oxygen. But when you have nucleophiles that are often considered quote-unquote softer, they are going to lead to, again, there's a molecular orbital answer behind it. I don't really want to get too much of the details behind it, but when you have something that's considered a softer nucleophile, it's going to lead into where what we consider the lower lying LUMO, and so there's a molecular orbital reasoning behind this that would lead to addition at the beta position. Okay? In terms of you guys remembering it, with the exception of Grignard's, what we're primarily going to see is addition 1,4. And so again, you can sort of rationalize that thermodynamic argument. The product in this case has a ketone, for example, and the product in this case doesn't, if that's how you guys want to rationalize it. But there is a more molecular orbital answer behind it. Okay? So that's simply to just show the difference in reactivities of nucleophiles that we've been used to with alpha-beta unsaturated carbonyls. So there's these two competing reactivities of alpha-beta unsaturated nucleophiles. And it turns out that in the case of enolates, enolates will react with alpha-beta unsaturated carbonyls through the 1,4 mechanism. And this is a reaction called a Michael addition. Okay? Okay, so if you take your standard ketone and you treat it with LDA, and then you subsequently treat that with we can go through the mechanism of this. What's going to happen is, first and foremost, we're going to generate the enolate. Yes? So the mechanism for addition, not following. Well, the argument is it's complicated. It's actually you have to go to like molecular orbital theory. You have to go deep into like molecular orbital theory and sort of explain where the lowest lying LUMO is in a given system, which would take an entire class, or maybe an entire course. But the thing is that the sort of, I'm trying to simplify it for you and just sort of point out, I think the important take-home lesson here is that there are competing reactivities of alpha-beta unsaturated carbonyls. They can react 1,2 or they can react 1,4. In some cases, when you have a really charged nucleophile, like alkyl lithiums, alkyl grignards, they happen to add 1,2. This is a hard argument. It's not, again, I'm not going to get into details, but I'm just sort of telling you from that standpoint. But there are some that add this way. But usually, what will happen is they'll actually add in 1,4. And the reason for that is where the lowest lying LUMO is of the system. But again, to sort of make more sense to you guys, or perhaps rationalize it, it's not this, but I'm just trying to help you guys remember. The product here forms a ketone. The product here forms an alkene. And you guys have seen time and time again that ketones are really stable, so you can sort of think about it as a thermodynamic argument. So I'm just trying to give that to you guys. That's not actually the reason, but it's at least one way that you guys could rationalize it. Okay? Okay, so in the case of a Michael addition, what's going to happen is, again, you're going to generate that enolate, and this is where we begin to sort of push electrons, and hopefully by this point, you guys are pretty good at pushing electrons. I heard somebody laugh. Because what's going to happen is, I'm just going to sort of skip over a few steps. Again, you can draw the resonance intermediates if you want to, but what's going to happen here is you're going to add in, and just like we showed over here, you're going to add to the 1,4 position. Okay, so that's where it's going to attack. Okay, if we want to push the arrows throughout this, what we're going to generate is the enolate. Okay, bless you. Okay, so this is this carbon. This carbon is the one that has the R3, right? Because we're making this bond, right? That bond. So now this carbon has the R3. Oh, sorry, there we go. Okay, and so we're going to get to that enolate, right? And what's going to happen is that this is going to, upon working this reaction up, what you're going to get to is this system that looks something like this. Okay, so again, keep track of the carbons. I think it can be very easy for you guys as you're drawing these to lose track of your carbons. So just make sure you map them out, right? So if you wanted to start drawing, we're making this bond here, which is going to be this bond there, right? And then what's happening is the double bond that was here is becoming there to make the enolate, right? And so I think that when you start drawing as many electrons, this is oftentimes where you guys can start making some mistakes because a lot is going on there. But formally, this is a Michael addition. Okay? One reaction that's actually a combination of a Michael reaction and an Outlaw reaction that's been really important for synthetic chemists is a reaction called the Robinson Annulation. And all that a Robinson annulation is, as you can see, it might look a little bit complicated when I draw it, but formally all a Robinson annulation is going to be is a Michael addition followed by an intermolecular Outlaw condensation, okay? And so I'll show a kind of famous example of it. This is one that I actually worked in when I was in graduate school, and it's the one that's often brought up a lot when you're talking about the Robinson annulation. But if you take this or some type of beta diketone compound, and you first take this molecule and you treat it with LDA, or actually you don't even need LDA, I think it's potassium carbonate, followed by, let's say, methyl vinyl ketone, or let's say ethyl vinyl ketone, okay? No, you said, well, that's, I probably should have drawn, the aldol is one step. I shouldn't have said 1 and 2. I should have said I, double I. It's one pot. You add the base, then you add. So when I draw this sort of semicolon, what I mean is you add this and you add that. So, and then the second step of what you're going to do here is you generally take it then and you treat it with, I think in my case I actually use just acid. I think I just treat it with camphor sulfonic acid. and an amine because I was doing enamine catalysis. But technically, you can do it for keeping consistent. What we'll say is LDA again for this, and then we will say blue aqueous workup, acidic workup. Okay? Yeah, I saw a couple hands. Yes. Oh, Robinson Annulation. Okay, so there's only 10 minutes left, so I'm gonna make this one because I want to get to one other class of reactions. So what I'm gonna do is I'm gonna show you guys the product of this reaction, and this is gonna be homework for you guys. So I want you guys to sort of try to figure this mechanism out on your own. Okay, and we can go over it first thing next class. The product of this reaction is that compound there. Okay, so it might look complicated. This is a molecule called Wheelan-Miescher ketone. And if you look at the sort of structure of steroids, for example, they often have this sort of 6-6 ring system. So a lot of times what early synthetic chemists would do is they use a lot of this stuff to build up and actually make a variety of different steroid analogs. So again, I'm telling you the first step is just a Michael addition. The second step is an Outlaw condensation. You put the two together, and what you get to is this molecule there. So go ahead and try and, at home, try to work that out on your own. And we'll go over the mechanism on Wednesday. All right, the last sort of class of reactions that's sort of within this, a bunch of reactions that are all the same, are sort of Claisen condensations and Dieckmann okay? So Claisen condensation and the Dieckmann condensations are literally the exact same reaction. It just turns out that Claisen condensation is the intermolecular, whereas Dieckmann is the intramolecular, okay? And all Dieckmann condensation is it's the reaction whereby you take a ketone and now the sort of carbonyl electrophile that you're treating it with, instead of it being an aldehyde or an alpha-beta unsaturated. So we've seen enolates react with aldehydes. We've seen them react with alpha-beta unsaturated. Just showing you an example where they react with an alpha-beta unsaturated followed by an intermolecular addition into a carbonyl. This one's going to be, I'll put double I this time. Yeah, it shouldn't have been one step in the other. It's all in one pot. That's going to be the addition into esters, okay? Now this is where something's going to be a little bit different than what we've seen in the past in terms of nucleophiles adding in to esters. So in past, when we've had molecules react with esters, what happens? It adds in once, eliminates the generated ketone, adds in again, ends up with the alcohol. Dieckmann condensation, as we'll see, only adds in once, okay? And we'll hopefully understand why in a moment, right? So when we take and we treat when we go ahead and we treat an enolate with an ester, what's going to happen is the product that we form board space time, I'm just going to add it up and it's going to kick out. So I'm just going up into the carbonyl, collapsing down. Might look complicated on the board, but just follow it through. Electrons are going up through the carbonyl, back down. We're kicking out ether group. So we're using, in this case, an ethoxide. Okay, and we're going to get this beta-keto 1,3-diketones. Now, one of the things that we really haven't discussed And perhaps this is one of the first times that we'll see this, right? But 1,3-diketones or 1,3-keto esters, or any time you have these carbonyls with like a skip CH group in them. I didn't show this before, but I'll sort of show it to you guys now because it sort of makes sense within this. But in general, we rarely see, in terms of the enol keto tautomer, we almost always see it existing in the keto form, right? And again, the reason for that is that the keto form... Guys, can you close the door, please, or quiet it down? And again, the reason is carbonyls are much, much more stable than, say, alkenes. However, what do we notice about the case of the 1,3-diketone? Sort of relevant to what we were just talking about earlier. Yeah. Right, it's a conjugated pi system. And so I've sort of shown, up until now, I've sort of shown these 1,3-diketones as 1,3-diketones. But in fact, the lofin exists much more in the enol form. Again, because now you have that conjugated system. Now you've got something much more stable. Now you've got something that almost seems like, in a way, right, it starts to look more like an ester again, right, in terms of the resonance forms, right? And that same reason that the ester has that resonance stabilizing property, we can imagine a system here where you can resonate up into the other carbonyl, so it's sort of through an additional pi system, but it's sort of like a skipped ester, if you will, sort of like an ester that's just separated by this carbonyl. And so, again, Claisen and Dieckmann condensations are good ways to generate these 1,3-diketones, okay? Now, in the remaining 2 to 3 minutes, I just want to go back to the very first thing I talked about in class. Again, we've just seen carbonyls reacting with enolates. And one of the very first things that I sort of told you guys is one of the ways you can control chemical reactions, okay? Now, let's see if I have time to go through this. So what we talked about was how if you have a molecule right? If you have a molecule like this, right, or you have a molecule where you want to react with this carbon over, say, for example, this carbon, you'll install the ester there, and you'll go through that sequence of events, right? So you just refer back to the initial stuff that I talked about. The Dieckmann condensation will begin to allow us to get entry into these 1,3-diketone systems. So that's where it really becomes valuable. So I've sort of shown an R1 here, right? But if that R1 is instead, for example, actually, where did I see it before? We saw it here, right? A system like that. So if instead that's our initial enolate, right? Sorry, this would be the R. Okay, so what we're going to do is if this is your... Sorry, guys. I'm getting distracted for a second. Okay, so if this is your ester that's going to be here, right, that's going to be that one there. Okay? And if we take it through the enolate Dieckmann condensation chemistry that we've seen here, so if we make this enolate and then treat it with this compound here, this ester, now we can begin to get these types of structures here. Okay? And so now we want to start making functionalization of that carbon, we can begin to do so in a selective way and then get the decarboxylation. So the Dieckmann condensation can really be our entry into this sort of initial system that I talked about. Okay, so with that, I think that covers much of the enolate chemistry. Actually, that gets us through all the enolates, so it ended up working well. So, but it was all additions of enolates into some carbonyl. That's all it really broke down to. Aldehydes, the condensation, alpha-beta unsaturated, esters. Okay, and next week we'll talk about enamines and their ability to do these kind of things. All right.